Hello everyone. I'm going to be talking about a new project that I started thinking about fairly recently. My name is tale-Hossam. I'm a postdoc at TUDAT. So I'm going to be talking about free precession in undriven warps. So these are warps that are not caused by a companion in the bending wave regime, so thicker disks. And I'm only going to be looking at it for gaseous warps, so alien gas disks. And obviously this has been looked at many times before, but we have missed some things because this is one of those problems that's only ever been studied in SPH, or almost only ever been studied with SPH, and that caused us to miss a few things, hence the cautionary tale. It's supposed to be a slightly provocative talk, so if you feel the need to yell at me at any point, please go ahead. A bit of disclaimer before, this image here has nothing to do with what I'm going to be talking about. This is dusty warps, which produce very nice pictures, but this talk is only about gaseous warps, which when they're thick, it's just not as easy to produce nice images. And I don't have any nice images for you. So, so there you go. Okay, I have to click. Right, so it's a bit of an echo. I'm muted.
Yeah, you're calling.
Sorry, yeah. I muted. Sorry. Right. So I did my PhD in Leicester many years ago, and Leicester is one of those universities where pretty much everyone does SPH. And whenever the topic of SPH versus grid codes is brought up, you always hear some of these arguments, and they're all very well motivated. And so some of the arguments of SPH versus grid codes is that for SPH you don't have any preferred dimensions. So if you have a warp disk, it doesn't want to align with your grid direction. You don't need to worry about any boundary conditions with SPH, any waves reflecting off the inner or outer boundary. Excellent conservation properties, certainly if you use global typeset, but also if you use individual typeset. Galilean invariance, you can model a problem with SPH and then give all the particles a very high constant velocity and it will produce exactly the same solution. That's not the case for grid codes because you have implicit numerical dispersion that is proportional to your advection velocity. And finally, you have automatic adaptation. You have resolution where you have mass, although that can sometimes be a problem. That's why we need things like APR and so on. For warp simulations, the first one is actually the most important because if you're really modeling the warp, it's very important for you to preserve the warp and not to have artificial alignment with your grid. So it's very important that you don't have any preferred direction, and that I think is the reason why most people who have looked at warp disks have done that with SPH rather than grid codes. And we always held that belief that this is the primary problem if you do warps with grid codes. But so there's this paper last year, carrying Kimmig and Dullemond almost exactly a year ago, who started looking at that closely. So they were looking at warp disks with 5A3D, so grid code, and that difference. And the first thing they wanted to test is actually exactly that. So they start with a flat disk, not warp, but just misaligned with respect to the grid. This is the grid, spherical. You chop off the top and bottom bits. And this is a flat, smooth disk. Nothing should happen. Anything that happens, any alignment that happens is completely numerical. It's not physical at all because it's just a flat disk. Nothing happens. And so they run that test, and what they see. So here they look at two things. So this is the inclination, and this is the precession angle as a function of time. And so this has always been our belief. You will align with the grid. It does seem to be happening, but it turns out to be a very, very minor effect. It's only 1 degree artificial alignment, as it were, for the lifetime of the simulation, a few hundred orbits. So this is not what we were expecting. We were expecting this to be a drastic is the main problem with doing warps with grid codes. It turns out to be a very minor thing. But they did recover something that's a lot more problematic. You have an artificial precession that's almost 70 degrees or so, or 80 degrees, throughout the lifetime of simulation. And that's completely artificial. That's still just completely flipping for no physical reason. So this is sort of counterintuitive. We did not expect that. SPH people will always tell you this is the problem, but it turns out there's another problem that's a lot more important. It's bad news for grid codes, obviously. You don't want 70 degrees of rotation in your simulation without a physical reason. But then they looked at different resolution for the same thing. And it turns out it's actually a very easy problem to fix. These are different resolution. And it turns out, so if you look at this green line here, you only need to increase the resolution in the vertical direction to completely get rid of this numerical precession. So you don't need to use all your volumetric, to increase all your volumetric resolution, just one dimension. It's a lot cheaper. So it's a very manageable problem. This is one of those things, one of the first things that this paper completely changed my view on this. And then they start doing actual warp disks. So after testing this artificial grid alignment, you start with an actual warp. So around a single star, no external torque, no binary, no lens steering torque. And you just look at the warp propagation inwards and outwards. We have a lot of work, theoretical work on this. We understand this. We know what to compare it with. And they do retrieve an inclination profile with time. That is what we expect. I'm not going to show it here because there's nothing surprising about it. What is surprising is that if you also look at the precession again, so these are the precession profiles as a function of time, the two different viscosities, 10 to the minus 5, you can't see it from the zoom thing, 10 to the minus 3 and 10 to the minus 2. And the colors are different radii in the disk. So blue is the inner part of the disk, and yellowish, greenish is the outer part of the disk. And you have this very peculiar precession profile where the inner part is precessing in one direction and the outer part is precessing in the other direction. That's completely unforced. That's why I call it free precession. And we've never seen anything like that in SPH. Now, the question is, do we trust you to ask questions?
Yes, we have.
Yeah? No, okay. I should have put this came out. So Ludato and Price have seen free precession in diffusive disks. That is very similar to the new 3 term, which we do expect from PE, but this is bending wave regime. This has never been reported before. It's completely different, and it doesn't quite match the new 3 term. So I should have put a slide because I should have anticipated this. So this is not something that we have expected before. And one of the reasons when I saw this first, the reason I expected that we missed it in SPH is because the effective viscosity of SPH is more like this than this. So you can very easily miss it. In fact, the floor of viscosity is normally even higher than this. So it'll be damped, this motion will be damped very quickly. Another thing to look at is the dashed black line. So this is the precession of the angular momentum vector of the entire disk. And you can see there's some secular effect here, which they do say in that paper is probably numerical. It's not physical. So the argument is that these oscillations are physical, but this slow thing is numerical. I was like, well, how do you know? Like, how do we trust any of this? And why did we not see an SPH? So I set out to try to do this with SPH. And I started with simulation with 500,000 particles, sort of fiducial, what people normally do with the dynamical range, and tried to produce the same exact plots. So I used alpha as 10 to the minus 3 as input in my simulation. I know that the alpha that we get is actually a lot higher than that, more than an order of magnitude. Several people have tested this many times. But I just wanted to try. And so what I get with 500,000 particle is this sort of thing. If you already know what's going on, you can convince yourself that you're seeing it, but you can very easily, if you don't know what's going on, you can very easily dismiss this as just relaxation of the initial condition. Right? It gets done very quickly. Luca gave a talk on the Thursday about all the artifacts that you can have from the relaxation of the gas and the initial conditions. So go up in resolution, which also means you go down in effective viscosity. Did 4 million particles, so factor of 2 in linear resolution, and this is a lot more convincing. So again, you have to really know that what you're looking for, but this is the fact that it goes higher with resolution, not lower, convinced me that this effect is physical. The other thing is that if you look at the dashed black line, it's exactly at 0 for both simulations, actually. So this is something we do expect. We know that SPH is much better at conservation of angular momentum, even with individual time step. So this is something that SPH was actually a lot better than favour. And if we put this again, same figure, just to compare. So this is an error, and the oscillation of physical is exactly what we see in SPH as well. So it sort of confirms this, but it also confirms that we missed this because we just never tried it with the grid code before. Another thing you can note is that this is actually, so this is meant to mimic this, but it's closer to that, which again is another independent evidence that the flow of the viscosity that we have is closer to the 10 to the minus 2. It's very hard to get 10 to the minus 3 with few million particles. This has been tested with different ways, and it's something that bothers me a lot, something that I wanted to moan about here in that conference. So no matter how I test it, the flow of viscosity is around 3 or 4 times 10 to the minus 2. So we miss things that primarily happen at low viscosities. So what's causing this precession? Well, we know from linear theory, Luber V 2000, these are the equation of the 1D equations for the propagation of warps. So here's the angular momentum vector, G is the internal torque, and this is the precession term that's due to any external torque you have, a binary, length steering, whatever. We don't have any of that, so this term is exactly 0. But you can see in the G equation, there's another precession term with a coefficient that's the amount of detuning you have from the gas orbital frequency compared to the Keplerian or the epicycle frequency, which is Keplerian in our case. And so whenever omega G is not exactly Keplerian, you'll have some detuning, which will cause a precession. And I think that's exactly what we're seeing. And so in our case, it's actually for a thick disk, you have a pressure support term, and so omega G is different from Keplerian. And that will source the precession term that we're seeing. This is our initial sort of idea. If that is the case, then we should be able to reproduce it exactly with a 1D code, and that's what we're working on at the moment. So we hope to be able to produce this with 1D. You just put in the detuning. There might be other complicating things. There might be some nonlinear interaction. There were work from Callum Fairbairn and Gordon Ogilvie on a weakly nonlinear theory of warps, and there might be interaction for the low K modes with the disk thickness that can also cause some sort of precession. So we're a lot of things to discover here. Nearly out of time, but I wanted to take home messages. There's only really 2 things that I wanted to stress, is that even though we have very good reasons to believe that SPH is much better adapted to this problem, we should always be trying things out, because otherwise we miss things. And the other thing is that something needs to be done about the flow of effective viscosity in SPH. If we really want to understand protoplanetary disks and alpha is 10 to the minus 3, 10 to the minus 4, we need to know how to get there with SPH, and not a lot of testing has been done. A lot of papers claim that we have alpha to the 10 to the minus 3 in an SPH simulation when it's not. If you measure it, it will not be like that. It will be an order of magnitude more than that. So I think something needs to be done. And I'll stop here.
Are there any questions? It's probably a silly question, but if with Shamrock we go with the SPH scheme super high resolution, like billions of particles, do you think we will still have this 10 to the minus 2 problem? So you said no matter what you try, you always remain there.
Yeah.
What if you go 3 orders of magnitude more in resolution?
It's not a silly question. I think it's a very good question. I don't believe this is one of those problems we can just throw particles at. I think a higher number of particles would help. But I think if you ask any other person, you have different answer to that question. My impression is that we need to also use smoother kernels with higher truncation to minimize the reordering, because the reordering of the particles at the kernel level gives you a viscous-like evolution. We've tested that with things like the Gresham vortex and things like that, and you really need smoother kernels with more support along with more particles. So more particles, but also bigger kernels, smoother kernels, Wendell kernels with more support, or quintic or whatever, but with more kernels in the wing to minimize the summation errors, this reordering. Not a smoothing length. Will limit. So the smooth in SPH means that the particles have always to maintain a smooth distribution, and they do that by moving independent of the flow at times to maintain that order. That's a good thing. That's how we have all the conservation properties. That's how SPH gives you a very smooth density estimate. But a drawback of that is that the particles do not always move with the flow, and that gives you a viscous-like evolution. And the way to minimize that is just having more particles in the same kernel. So that actually reduces your resolution at the same total number of particles. So you need to increase the total number of particles to compensate for that. So basically you need to increase both. And there will be a balance that we need to be sought for. We need to search for that. Please.
Sam, thanks for the nice talk. Could you please show again the equations? Yeah, that's one.
Yeah.
So you're saying basically that you have this additional precession because the angular frequency is not exactly the criteria one. But of course, here you assume that mu is depending on the radius, right? Because otherwise it would be just kappa would be equal to omega anyway, right?
Well, yes. So yeah.
And so if mu scales as a pressure gradient contribution scale,
well,
even there differences in the inner part, outer part.
Even if it's not a function of radius.
If it's a constant, I think that kappa should be equal to omega because it would be just proportional to omega k, right?
Kappa is omega k if you have a single star. The only deviations between kappa is a complete gravitational term. So this has nothing to do with pressure support. This will always be omega k, unless very close to the binary because of the binary effects.
Okay,
we can discuss it later.
Thanks.
Cheers.
Any other questions?
Dan.
Brief comment, which would be that seems like a great problem for Yana.
Yeah.
Like this is already set up in Shamrock, right? The warp and free warp is probably doesn't require extra physics, so it'd be a great one to just try to use your remaining hours on Aurora.
Absolutely, yeah.
Actually doing it at the moment. Not exactly the same simulation.
The main thing is just read a thicker disk for this, right? So you're doing black hole disks that are very thin in the diffusive regime. But yeah, for this, I mean, we know we can do alpha of 0.1, the regime that we know we can do that with SPH, no problem. You've looked at that 15 years ago and absolutely convinced we have no problem in that regime. It's the thick disk regime that we struggle with alpha of 10 to the minus 3, h of r 0.1, 0.15. That's the regime we struggle in, not the black hole regime. So it's a bit different from that, but the same physics.
Actually, I have a question. So related to the alpha bit in general, there are some estimates that basically it should scale as the number of particles per scale I, roughly. As such, like if you are multiplying your resolution by 100, your alpha should drop by a factor of 10. You say that it's maybe not the case because of the local reorganization, but if you bump the resolution, the local reorganization is also like more contained within a smaller volume. As such, why the alpha shouldn't go would the alpha drop by a factor of 10 or less?
Yeah, okay, so the scaling you're speaking about is correct. Once you're above the floor, you're not hit by the floor. What I'm speaking about is a floor that you hit just from the kernel-based forces. That's not the scaling that you get from alpha AB to alpha SS. That's correct. But what I'm saying is that there's an effect on top of that you only hit when you want to do very low viscosity disks. So it's not just the scaling, it's not just the resolution effect.
But then the reorganization forces also of the less importance if you bump the resolution as such. The floor also should move down, maybe not at the same rate as the.
Even if it is, it won't get you there as quickly. But if you have 10 billion particles in your simulation, but still the kernel is only 55 neighbors. Those 55 neighbors have to do the same work to minimize the noise at the kernel level.
You say, yeah, okay.
So you need to increase the neighbor numbers within the kernel.